Hello friends, my name is Vivek Sharma. Today we can cover this interesting problem that's called binary tree vertical order traversal. So let's do this. Let's first of all try to understand what that vertical order traversal means and how we can solve this problem in the next part. So generally I try to divide this video session in two parts, like first of all to understand the problem and to just collect the facts and requirements. Once we have the grip on the problem, like what the problem is asking us to do, then we can just think of the different approaches, and we can just note down all the thoughts and the implementation, how we are going to solve this problem, and then finally we can write the code. So writing the code should be very end part. So uh, uh, I try to focus more on the requirement analysis and then the implementation part, and that's how we should approach the problem. So let's jump into it without wasting more time. So in this problem, it's saying that vertical order traversal we need to find of its nodes values from top to bottom and column by column. All right, so this is the first example. So let's do this. Let's quickly draw this binary tree here. So 3 9 20 and then 15 and 7, right? So if I draw this diagram is the binary tree that has been given in the first example. So let's see what that binary tree vertical means, and let's see if there is anything in the node section. Okay, so there is nothing in the node section. All right, so now if I choose some different color, let's say red color. So this is my first column, this is my second column, this is third, and this is fourth, right? I am here just drawing some vertical lines, that's it, right? So this is zeroth index, this is first index, this is second index, and this is third index. So if I have to collect all these nodes index wise, vertical order index wise, then what would be my output? It would be 9. So 9 on the zeroth index, and at the first index I have 3 comma 15, right? 3 and 15 is there in the first index. At the second index I am having 20, and at the third index I am having 7. Okay, and this is intentionally I have drawn this binary tree that you can see here that 15 is just below than 3, and that's how basically we should draw the diagram to understand this problem, right? So that we can see like what is the scope of this first index, right, or the second column, and what is the scope of 20, or the second index, right? If something is there on the left part of 7, that will come under 20, and that will be covered on the second index, right? So this is just to clarify this. Now let's see. So the output is 9 3 15 27. So looks like we are on the right path. All right, so this is one way to understand this problem. And that's how we need to understand this problem. And the column by column, if the two nodes are in the same row and column, the order should be from left to right. So this is just a node section, right? If they are in the same row and the same column, then the order should be left to right, right? So left to right, we will just move from left to right while considering right. And what does that mean? Basically it's just nothing, right? So for example, for the first column, right? So first column, what we are doing, uh, 3 and 15 we are just taking, right? And 20 and then 7. So this is like a very basic example, and they have given like other examples as well here. We can make several examples and we can just try those as well, but let's first of all let's focus to understand this problem, and just to for the implementation part, like how we are going to solve this problem. So let's jump to the next section, and that is basically how we are going to solve this problem. So let's say this guy is root 3 9 20 and 15 7. All right, so this is again I have drawn the binary tree here. Now let's first of all collect the requirements or the observations what we are observing by seeing this problem. So a couple of observations here is basically, if we see here the closely, first of all the index, basically the column or index. So definitely we need to keep a track of the indices as well. So every index we should know, right? So 0, 1, 2, 3. So these index we should know. Uh, that's one observation, right? Another observation is basically we are just going from left to right, obviously, right? So whenever we are maintaining this indices, basically 0, 1, 2, 3, we always have to keep a track of the leftmost, and we have to always keep a track of the rightmost. Why we need to keep a track of leftmost and rightmost? Because with the help of these pointers, the leftmost and rightmost, we can just collect these nodes to build our output and we can return, right? So this is like second. So let me quickly note down what we are discussing here. First observation is basically definitely indices, right? This is, and basically indices, right? Second is basically we need to keep a track of leftmost, or in the simple term I can say min index, right? And max index, right? Max index. So these are the two observations we have seen so far. Now uh, min index, max index. So min is basically leftmost, max is basically rightmost index, right? And what was the other part? Other part is the just to keep a track of the indices as well. Now what approach we should follow basically to solve this problem, that's another thing. Definitely this is not going to be the depth first thing. The reason of not going to the depth first, because there is no pattern or there is no intuition that we are getting that we have to go deep in one direction and then come back, right? There is no such indication in the problem itself. So we can just cut that option from our list, that it is not depth first. Now let's come back to the breadth first. Can the breadth first work? So let's explore this option as well. So breadth first, basically what we do in breadth first, generally we just go sequentially and we just traverse all the corresponding neighbors, right? So if we follow the breadth first pattern, we need to find another pattern even before jumping to the breadth first. So another here observation is every node is having the access of its left child and right child. Of course every binary tree is having the same property, so every node is having the access of left child and right child, and this observation we can use in the breadth first manner. So whenever we see that every node is having left uh, the access of the left child and the right child, what we can do here, whenever we traverse each and every node, we can just maintain our min index and max index, right? So the second observation was min index and max index. So what we can do, every node, whenever we find, we can just say okay, what will be the minimum? So for let's say for example 3, for the root, this is the root, right? 3. So for the 3, what is the minimum index? So minimum index will be for that basically 1 minus 1, and that is 0, right? So this is the 0, and 1 plus 1 is 2. So the right side child would have the max index for 3. And what will be the min index and max index for 20 at the index 2? That will be 2 minus 1, and that is the 1, right? And 2 plus 1, that is the 3. So if we can use this kind of a thing, like every node is having the access of left child and right child, in other words every node is having the access of min index and max index, then we can maintain basically our min index and max index for each and every iteration. And once we have this min index and max index, then we can simply build our output from min index to max index, and we can collect all the nodes, right? Now uh, whenever we are going to collect the nodes, we need some kind of the data structure from where we can store all these nodes, right? So I think the easiest part here is easiest way to store all these nodes, I would say, is like just take a hash table kind of the data structure, hash table data structure, and then just put all these nodes in the hash table based on the index, right? So let's say zero index would have 9, first index would have 3 and 15, and second index would have 20, and third index would have 7. Why this is the easiest? Because it's, we can just imagine the key value pair. So key is here the index, and the value is basically the corresponding node, right? And it can be the collection of nodes, so we can say that value can be the list itself, not the individual node, but the list. Value can be the collection, right? So it can be the list of nodes. All right, so once we can store this in the map fashion, right? And then we already know that we are maintaining this min index and max index for every node, and at the last we know that what is our min index and whatever the max index, we can simply just collect all these nodes from min index to max index, and then we can just build our output. So let's do this. Let's try to see. So these are the observation indices: min index, max index, and third is basically hash table, right? So I'm just writing the hash table as well, right? And of course, another observation. So this is the fourth observation, I would say, BFS. So why BFS here? Because we are just going, we are just trying to explore the neighbors, right? Why, how neighbors? Because I mentioned, like for example, we are on the route 3, we are saying, okay, what is the left and right? Once we explore those left and right and we just store min and max, then we are just going again to the left side 9. Unfortunately it does not have any children, right? It does not have left and right, so it will not do any traversal. But for 20 it is again having left and right, so it will just explore its children, right? So it will explore 15 and 7 in this particular case, right? So that's why I'm saying that it is the breadth first search. So if we are already aware about the breadth first template, we can just apply the same template here as well. Okay, so so far these four observations. Let's go ahead with these observations and let's try to uh, uh, implement this these assumptions, and then let's go from there. Okay, so let's see what is our output list here. So let's say our output list is here. I am just mentioning is as res, and let's say if root is null, right? Then we are not going to do anything. We are just simply returning this list. That's it. Now, as we mentioned that we have to maintain one map, so I would take map, right? And the value of course can be the list as well, right? Because here we have seen in the previous page basically, if I go to the previous page, this at the first index it's having the 3 and 15 as well, right? So it's a two nodes, right? So 3 and 15. And what does that mean, 3 and 15? That simply means basically it can be the more than one node, so that I have to take the list as a value. So list of integer, and this is map new has map. All right, so we have taken map, we have taken we have handled this base case whenever root is null, just returning the empty list. Now let's take the queue because it is the BFS, right? So let's take the queue for the these nodes. So queue equals to new linked list. Queue is nothing but it is a linked list as well only, right? Because it's a breadth first thing. So the nature of is the breadth first, but implementation is basically the linked list, right? For the queue data structure. Now initially just have the root node in the queue initially, right? And as we have seen in our observation that we need to maintain the min index and max index, or in the simpler terms, if there is a confusion with the min index or max index, let's feel free to take the left index, leftmost index, or rightmost index, right? But here let's make it consistent between the whiteboard and the code, right? So min index and max index, we are initially taking 0, right? So let's take the 0 initially, right? And then we will just calculate what is the minimum index and maximum index. All right, so these are couple of the things. Now another thing here is we need to let's go back to the observations page. So at the first observation, we have to maintain the indices as well. So we have to know that which node is having at which index. So looks like we need to maintain another queue for the indices, right? Otherwise, how we are going to determine that which node is having at which indices? So let's go ahead and do that as well. So let's take another queue for the indices, right? And this is, let's say, indices, and then new linked list. And initially, let's say, insert 0 in this indices. And now let's apply the BFS template. So what the BFS template means, that this is kind of the standard template that we can apply in most of the BFS kind of the approach. So we just check whether queue is not empty. Then what we say, we just check the size, right? What is the queue size? And once we know the size, we can just have this loop, and then we can just run this loop till size, right? And here we can just poll basically from the queue that what is our node. And in standard BFS thing, what we check, like if left is not equals to null, then go ahead and traverse the left side. If right is not equals to null, then go ahead and traverse the right side. Okay, so let's go ahead and do that as well. So queue dot offer node dot left here, queue dot offer node dot right here. All right, so now let's do the here we have seen, as I explained earlier, that min index and max index, and for every node we can just calculate what will be the minimum index and maximum index. So again, to reiterate the same thing, let's say for example 3, the minimum index would be the 1 minus 0, and max index would be 1 plus 0, because it's having the axis of left child and right child. So left index and right index, left index would always be current index minus 1, and right index would always be current index plus 1. So let's go ahead and do the same thing here as well. So indices dot offer, and we will poll the index as well, right? So let's go ahead and do this current index. Current index is indices dot poll, right? So indices dot offer would be what? Current index minus 1 in this case, and similarly indices dot offer current index plus 1. All right, so let's go ahead and let's calculate the min index as well. Why min index? Because this min index would be basically the minimum. So let's say we are at the index 2, right, and it's 20. This min index is 1, but 1 is not the min index. This is the min index for 20 for the at the index 2, but in actual min index is 0, right? So we have to make sure that our min index is correct, and max index is also the rightmost. Min index is the leftmost, and right index is the rightmost. That have to make sure. Why we need to make sure? Because in the end we are going to build our output list based on the min index and max index. So hope this is clear, right? So let's go ahead and do that. So min index would be math.min here, and min index comma left minus 1. So not left, but it would be current index minus 1. Okay, similarly we can have this max index as well, math dot max index comma correct index plus 1. All right, so this is done now in the breadth first manner. Now we need to populate the map as well, because this is the map that we will use to build our output list. So let's go ahead and do that. So this key will be the index, right? Current index, and new linked list. And we want to make sure that each index basically is having one list, right? We don't want to build a lot of list, right, for each index. So let's, if I go to the back to this page, at the first index we can see that it is only one list, and that list is having 3 and 15. We don't need the separate list for 3, right? So we don't need like 3 and then comma and the list 15, right? This is not the right way. So what we will use here, we will use a put if fsend, right? If fsend will make sure that it's not having the existing list, right? And now let's go ahead and do this current index and then dot add. Basically what we are going to add, node dot val. So this is how what we are doing, we are just building the map. So in this basically here 9, so key is 0 and the value is 9, one key is 1 and the value is 3 and 15, key is 2 and value is 20, and key is 3 and the value is 7, right? This is how we are building, right? K and v. So key and comma value, value is the list, right? If it does not matter, list may have single value or multiple values, right? So in this case, in case of 9, list is having only single value. All right, so this is how we need to do this. Once we are able to build in our map, then basically we are already having the access of min index and max index. Then let's go ahead and utilize that as well. I is less than equals to max index. Why less than equals to? Because max index is also index, it's not length, right? So index, we need to make sure that each and every index we are covering. So here the third index also we are covering, right? So just make sure it's index, it's not the length of array, right? So that's why we are doing the less than equals to, and I plus plus, and then res dot add map dot get index, right? So because these are the index, right? And then go ahead and return res. So this should be the basically code that we are trying to do it here. Let's quickly analyze basically complexities as well. So time complexity, this would be the order of n. Why order of n? Because we are going through each and every node here for our algorithm. And space complexity also, we are maintaining all these lists, all these nodes basically in a hash map. So I would say it would still be the linear complexity in the space wise as well. Let's quickly check if there is any compilation errors. So I missed the semicolon here, let's quickly correct that. um, okay, I made some mistake in some other line as well. Let's quickly correct that as well. So line 41. Okay, so so I missed the semicolon here as well as a part of for loop syntax. So let's go ahead and correct here as well. And indices dot offer, so indices, and then int cannot be converted to the tree node. So this is my mistake, it should be integer because this is the index, right? This is not the tree node. So we have two queue basically, one is for the tree node and another is for the index. So that's what we are doing. So looks like this is giving the right output for us, right? I will go ahead and quickly submit this one, and I would again just revise like what can be the good summary and what can be what we discussed so far, so that it's not going away anywhere. So let's quickly just quick recap of what we are trying to do it here. First of all, the problem is basically itself the vertical order traversal. So vertical order traversal, we don't need to be scared, we just need to move bit by bit. Means we just need to observe all the observations and all the facts and all the requirements involved in this problem. And couple of observations that we have come through here is, first of all, we just draw all these vertical lines for all these nodes, and we are trying to collect for each and every index these nodes in the form of this, like key and value. Key value basically came into the picture later on, but for our facts basically we need to check like what are the indices, what is the definition of the indices here. The definition of indices here is the vertical line. So each vertical line is having the uh, corresponding nodes, as we can see here, right? So each vertical line is representing the particular index, and that each vertical line is covering some set of the some set of the nodes that we need to take, right? Another observation is here is basically because we have to display our output is from the leftmost to the rightmost, right? So important observation here is basically we need to maintain the min index and max index, right? That's what also we need to maintain, so that in the end we can just use that min index and max index to build our output, right? So that's what we mentioned here. Another is the observation here is the hash table. Why hash table? Because uh, if we are using this min index and max index, we need some storage, or we need some kind of collection or something that we can store, that we can tie each index with the corresponding nodes, right? So in this kind of the scenario, hash table is a little bit more convenient, where we can have key as a index and the value can be the corresponding list. And once we store all these nodes in the hash table, then we can easily iterate through that hash map or hash table. Hash table is a data structure and hash map is again the API name in the Java. So don't be confused between the data structure name and the API name, right? So we can use that hash table to build our output. So that's why we are taking the hash table. Now another important thing is here the BFS, right? So uh, this is the binary tree. So we are the flavor of the problem is not depth first. We are not going in the one direction. We are using here the BFS, and in fact for the BFS we need to maintain two queue here. Why two queue? So one queue is definitely for the nodes, and another queue is for the indices, right? So indices also we need to maintain, otherwise how we will know that which index is having which node, right? And to stitch this indices for the corresponding nodes, we are using the hash map. So this is, I think, an excellent problem, where we can break down this problem to the different observations and different facts, and we can stitch those parts together. And then once we understand all these things, then I think the code should not be the big deal for here. I think, hope you enjoyed, and this might be useful for you. Thanks a lot for watching. Have a good one.